I'm Robert Brown, co-director of the Bioeconomy Institute at Iowa State University. Today I'd like to talk about carbon negative energy, which goes beyond zero carbon energy, as I will describe in my presentation. Let me start by distinguishing between carbon reduction and carbon removal. Carbon reduction is reducing the rate at which carbon dioxide enters the atmosphere from anthropogenic sources, while carbon removal is the actual removal of carbon dioxide from the atmosphere. The illustration is to indicate that the train has left the station as far as carbon reduction is concerned, and we need to look more closely at carbon removal. Climate policies, in fact, are increasingly calling for carbon dioxide removal and reliable sequestration. This includes the 2014 IPCC Working Group 3 report and the 2015 Climate Summit in Paris, which concludes that nations should work toward a balance between anthropogenic emissions by sources and removals by sinks of greenhouse gases. And I'd like to particularly concentrate on agriculturally based carbon removal. And this is the notion that let's harness photosynthesis to fix carbon from the atmosphere as soil carbon and plant material. Now, this map shows soil organic matter in the U.S. In the state of Iowa, we see a very dark region, which indicates there has been a lot of natural sequestration of carbon dioxide in the soils as soil carbon. We would like to boost carbon removal in agricultural lands through thermochemical processing of crop residues and dedicated energy crops. So we start with photosynthesis, which is going to remove carbon dioxide by the power of solar energy, converted into biomass. Some of that will also be used to generate soil carbon. We would propose to process the biomass, produce a variety of energy products shown here: electricity, hydrogen, biofuels, and bioproducts. There would be the possibility of sequestering some of the carbonaceous residue known as biochar into soils, along with the soil carbon generated by the growing plants. There is also possibilities of sequestering the CO2 in the geosphere. In this manner, we achieve a net carbon removal from the atmosphere. We would propose to do this by the thermochemical process of pyrolysis, which is the thermal decomposition of organic compounds under oxygen-starved conditions. The temperatures are usually in the range of 350 to 600 degrees centigrade. What I'm illustrating here is a pizza oven, and in fact, pyrolysis is a hot pizza oven. There are three products from pyrolysis. This includes gases that include carbon dioxide, carbon monoxide, and hydrogen. There will be solids. This is the carbonaceous material referred to as biochar. It also includes inorganic compounds as an ash component of the biochar. And there's also liquids, which we sometimes refer to as bio-oil. I'm illustrating here a gardener burning vegetable matter in his backyard, and you'll see the white smoke is actually bio-oil, which we would condense as a valuable energy product. But there's also produced biochar, the black material, in the pile of burning material. We're going to focus on producing bio-oil as well as biochar. This is the liquid condensed from the pyrolysis products. It's actually a mixture of hundreds of organic compounds as well as water, illustrated here. It has some appearances of petroleum, but in fact it is quite different. These tend to be polar compounds that are fairly reactive compared to nonpolar molecules found in petroleum. But there are a number of applications that have similarities to the use of petroleum. I'm illustrating here bioasphalt can be produced, as well as renewable diesel and aviation fuel from this bio-oil. The biochar is a carbonaceous residue from the pyrolysis biomass. As it's produced in fast pyrolysis, which I'll be describing, it is a fine material. We have investigated prilling it to produce a material that is easier to store and to apply to agricultural fields. Biochar actually achieves more carbon storage from these plant residues than letting it remain on the soil. So here I'm illustrating the fraction of carbon remaining over time, and these are very long times. We're talking up to hundreds of years. In fact, the green line shows a residue that would decay over the course of a couple of years, leaving very, very little carbon in the soils over long time periods, whereas the biochar is a very recalcitrant form of carbon, and after a very quick dip over the course of a year, the amount of carbon remaining with it stays constant over very long time frames. We're envisioning a pyrolysis biorefinery for the production of carbon negative energy. We would start with lignocellulosic biomass. This would include things like wood, crop residues, or purposely grown dedicated energy crops. We would pyrolyze these and then recover the pyrolysis products as a number of unique streams. We've been developing the technology over several years to do this. This would include unrefined sugars from the polysaccharides in lignocellulosic biomass, a phenolic oil that's derived from the lignin in the biomass, an unrefined acetate that comes primarily from the hemicellulose in the biomass, as well as the biochar. These primary products can be upgraded. We're envisioning first generation products. The sugars seem very natural to go to ethanol production. The phenolic oil, we've experimented with as I've indicated earlier, bioasphalt, but also marine fuels. The unrefined acetate is proved fairly difficult to economically recover, but left in the gas stream can be used for in-plant thermal energy production. And of course, the biochar has prospects for soil enrichment as well as sequestration of carbon. There are potential future products from the unrefined sugars. They're actually very interesting anhydrous sugars, most of them. And there are a lot of potential for producing pharmaceuticals, polymers, and alcohol to jet fuel. We're also looking at producing renewable diesel from the phenolic oil, octane enhancers, and bio-based chemicals. Eventually, the unrefined acetate has potential for the production of acetone, acetic acid, and biocement, as illustrated here. And we're doing some testing with the biochar and producing slow release fertilizers. We've also developed autothermal pyrolysis as a unique development in pyrolysis technology. As I mentioned earlier, pyrolysis is normally thought of as a process that takes place in the absence of air. The energy required is achieved through some form of heat transfer into the reactor. Heat transfer is a surface area limited process, and so as reactors get bigger, it gets more and more difficult to get thermal energy into the reactor. We've experimented with putting very small amounts of air. We're talking about stoichiometries that are in the order of 6 to 12%. This is actually lower than gasification. And this provides enough autothermal energy release to provide the energy for pyrolysis with very small penalties in the desirable pyrolysis products, which I will illustrate. Here on the right side of the slide, I'm illustrating the advantages of using an autothermal process in blue versus conventional pyrolysis in red. We're looking at the throughput of a reactor, tons per day, versus the diameter of the pyrolysis reactor. And we see that conventional pyrolysis, because of this heat transfer limitation, scales very slowly. Well, it goes as a square of diameter. But in comparison, autothermal pyrolysis is a volumetric process, and it releases, it scales as the cubic diameter of the reactor. This also has effects on the cost of the reactor, with the autothermal pyrolysis achieving classical economies of scale in the cost of the reactor versus the size of the reactor, the throughput of the reactor, compared to the conventional reactor cost. Here are some results from experiments that we have done in autothermal pyrolysis. The top Sankey chart is for untreated red oak. This is going to be a nitrogen-blown pyrolysis. It was somewhat less than 5 kilograms per hour for this 3.5-inch diameter reactor. It's showing here the breakdown of the various products. I want to focus here on the heavy ends, which is where most of the value, the sugars and the phenolic oil are, and compare that to autothermal operation, where we're putting in oxygen into the reactor at equivalence ratios on the order of 11%. We see almost a 3-fold increase in the throughput for the same feedstock of red oak in the same identical reactor, with only this change of the oxygen addition. And we see that there is a small reduction in the heavy ends because of this partial oxidation. Most of the exothermic energy comes from oxidation of the biochar. And so we've got almost a 3-fold intensification. In this case, we've observed even larger intensification for other kinds of feedstock. Autothermal pyrolysis achieves greater net carbon removal and higher net present value than conventional pyrolysis, even without putting carbon credits on the carbon removal that has been achieved. So what we're looking here on the left is the carbon removal measured in kilograms carbon per kilograms carbon in the biomass. We start with conventional pyrolysis of corn stover, comparing it to autothermal pyrolysis of corn stover, and we see a net removal of carbon, in this case measured as minus 0.33 versus minus 0.38 kilograms carbon per kilogram carbon in the biomass in the case of corn stover. We compare this for conventional and autothermal pyrolysis of red oak, woody biomass, and we also see achievement of net carbon removal. In these cases, again, the autothermal achieves a larger carbon removal than conventional pyrolysis. The real advantage of autothermal pyrolysis is achieving this net carbon removal economically. So I want to emphasize that we're showing net present value in millions of dollars for these 4 scenarios again. And this is without carbon credits. And we see that these are achieving a positive net present value for all of these scenarios except for the conventional pyrolysis. But in both cases, the autothermal has a slightly better performance. Based on our research to date, we prepared an application, Elon Musk X Prize Carbon Removal Program. This spring, we were notified that we would receive one of the 15 milestone awards. These are distributed across the U.S. The purple dots indicate where the winners are located, and we're highlighting our location. These are $1 million awards that are intended to help teams move toward application for the $50 million grand prize in the next couple of years. A demonstration scale autothermal pyrolyzer is under construction, sized to exceed the 1,000 tons CO2 removal requirement to qualify for the X Prize grand prize. The feedstock is corn stover. The technology is our autothermal pyrolysis technology, and it will be able to remove, if operating at capacity, of 1,000 tons of CO2 equivalent in less than 100 days. The demonstration pyrolyzer, financed by Stein Seed Company, is constructed as a modular system. Modules designed to fit on a flatbed truck are factory constructed, shipped to the processing site, and then assembled into an operational system. The photograph shows the various modules as they've been completed, including a biomass handling module, biomass conversion module, a bio-oil recovery module, and one for biochar recovery. There's a thermal oxidizer for emissions control, and then modules for the various utilities of the system. I'd like to end by acknowledging X Prize Carbon Removal Program for awarding a milestone prize to Iowa State University. We appreciate the vision of Harry Stein of Stein Seed Company in financing the construction of a demonstration scale autothermal pyrolysis plant and the engineering and construction procurement services of Frontline Bioenergy. Thank you very much.